Hello, good morning. This is an example of how you do the performance task for a convex mirror. Okay, so first of all, you have to make the lens axis. So you have to draw a line like this. Make sure that you have the line as straight as possible. Okay, second, you will choose a point from which you will anchor your compass. So I will choose a point somewhere here, and then you get to decide what would be your center of how far your center of curvature is. So in my case, let me decide it to be um 5 centimeters away. So I will measure 5 centimeters from here. So I want my mirror to be here. Okay, but obviously you can choose whatever value you want. I'm just choosing that as an example. So now in fact, class, please do not follow this example. So you anchor your compass here to your center of curvature, and you must make sure that your pen would be touching where you marked as 5 inch away, and then you make your curve. Okay, and then from there, obviously, you can choose your focus, and your focus is again just halfway between. This is your center of curvature. This is your vertex here. So therefore, halfway in between, which is 2.5 inches away, at 2.5 inches away from the vertex, so somewhere here, that would be my focus. Okay, and then from this point on, again, you can use this side to make it concave. You can use this side to make it convex. But as I told you, I will be using this as a convex example. So I will use this side here. And then let me choose a case. So for this one, let me choose case 5. So case, let me have another ball pen. Case 5. This is convex mirror. Object is between F and V. Okay? Only we have one problem. The problem is if we place the object between F and V, think about that, F and V. If we place the object between here, between F and V, then it will be reflecting off this side, which is the concave side, right? And it's not anymore a convex example. So therefore, somehow, you have to place it here, right? So what we can say is we cannot place it between F and V. We can say object is in front of the mirror, right? In front of the mirror, not siloam. And then what's the distance? At a distance equivalent to between F and V. Say pasabot og equivalent to between F and V. That means you take any distance that is between here, example that one, or this one, or this one, or this one, as long as it's between V and F, and then whatever that distance, you just simply transfer it, but in front of the mirror. Okay? So for simplicity's sake, let's choose 1 centimeter away from 1 centimeter away from the vertex. So remember, 1 centimeter away from the vertex, that's between V and F. But again, we cannot place it here. Otherwise, it will be a concave case. So we place it on the other side. So the object must be somewhere here. Okay? And then you get to choose the height of the object. So the height of the object, let me have the height of the object as something like 3 or 1.5 inch. Okay, so here 1.5 up to 0. That's my object. Okay, and again, I'm placing it here because again, we want the convex side. So we still use the word between F and V, even if technically there's no F here. There's no V because remember in a convex mirror, the F and V is on the inside of the mirror. But we'll just use that as a gauge for the distance. So technically the object is in front of the mirror at a distance that is equivalent to between F and V. Because this distance, which is 1 cm, this falls between F and V if it was inside. But again, we can't do that, so we have to place it outside. So we can say this distance is equivalent to between F and V. I'm not saying it's between F and V. It's equivalent to between F and V. Okay? And then, so here, what do we know? Well, we know that the F is 2.5 inches because remember, center of curvature to here, that's 5. So this must be 2.5 inches. How about the object distance? We know that the object is 1 inch away. How about the object height? Well, we set it to be 1.5 inch. Okay? So that is all we know. We know that the F must be 2.5 inches away. The object is 1 inch away in front of the mirror. The height is 1.5 inches tall. The object is 1.5 inches tall. And then from here, you can now do your ray diagrams. Okay? But again, what I want to do is I want to do the calculation, the mathematical method first. So remember, for us to do this, we have to find out what the Q is and the H prime. Those are the two important ones. Okay? So how do I do that? Well, first, I will have to solve for the Q. Okay? And again, I will just write it here, but I'm not sure if it's optimal because it will be messy. But anyways, so again, 1 over F is equal to 1 over P plus 1 over Q. So that means I want to solve the 1 over Q side. So 1 over Q is 1 over F minus 1 over P. So I want this to be one whole term. So I will join these two fractions together. So that's FP. FP divided by F is P. So P minus FP divided by P is F. So like that. And then again, I don't want to solve for 1 over Q. I want to solve for Q. So Q is just the inverse of 1 over Q. So therefore, I will have to invert this also. That's F over P minus P over F. And now you have the formula for solving for Q. Okay? So now I'll just replace Q is equal to, well, F is 2.5 inches. And then what's P? Well, P is 1 inch over, what's P? 1 inch minus, what's F? F is 2.5 inches. Okay? Now, there is some tricky part here. And the tricky part is we have to rationalize the distances. Okay? So for example, if we look at this and we say, well, the P, which is the distance from the V towards the object, because that's the object distance, if the P is 1 centimeter, 1 inch, right? So here to here is 1 inch. What is here to here? Remember, if you measure from here towards here, that's a different direction when you measure from here towards here. So now we invoke the concept of opposite directions. So remember in math class, when you go up, you assign it as positive. When you go down, you assign it as negative. Then when you go to the right, you assign it as to the left as negative and to the right as positive. So what that means is that these are opposite directions. So therefore, whenever we call one direction as positive, the opposite direction must be negative. Okay? So, if you look at our example, if we set this as positive direction, then here must be negative, right? I know that's confusing because, sir, sa math, sir, to the right kay positive man, to the left kay negative. No, we are not looking at it from the math perspective. We are looking at it from a real sense because if you have an object, you cannot really place the object inside the mirror, right? You can only place the object in front of the mirror. So therefore, that distance which is in front should be the standard. That should be the positive direction. So the distances that are inside the mirror should be negative because that's not the normal distance. You cannot place objects inside the mirror. There's no dimension in there. It's an imaginary space inside the mirror. So therefore, by logic, the normal distance should be in front of the mirror and the not normal distances should be inside the mirror. Okay? What that means is because the F is inside the mirror for a convex lens, so that's not the normal distance. So therefore, the focus is not the eye 2.5. It is negative 2.5 inches. This object is okay because that's the normal side. That's 1 inch. So this is negative 2.5. And for the height, if it's upright, that's positive. So sakto ni. If it's inverted, then that's negative. But in this case, we don't have to worry about that. We only have to worry about the focus. So the focus here is negative din eh. Negative 2.5 and also negative 2.5 here. And that's logical because remember you have two types of foci. You have real focus and a virtual focus. So what we're saying is a real focus is located in front of the mirror. So they are real and they should have a positive value. But virtual foci are inside the mirror and therefore that's not the normal side. Light rays cannot go there, cannot go inside the mirror. So it's an imaginary place. So it should be the not normal distance. So it should be assigned the negative distance or the negative direction in terms of distance. Okay? So notice convex mirror have negative foci while concave mirrors have positive foci. Okay, so now we proceed here. Obviously, I have to uh, multiply 2.5 this side first. So 2.5 times 1 is just 2.5. The negative sign remains. Inches times inches, that's inches squared over. Remember, this is 1 inch minus 2.5 inch. So therefore, the minus and the minus sign becomes plus, right? So therefore, this will be 1 plus 2.5. So this becomes 3.5 inch. And then the inches here cancels with one of the inches. Remember, inches squared is inch. So we'll remove the exponent. And then now all we have is 2.5 divided by 3.5, which is something like 0.71 inch. So let's just round it off to two decimal place for so that it's easier. So 0.71 inches. Okay? And then we can, from the Q, we can solve for the H prime because we have already solved this, which is 0.71 inches. And now we can solve for the H prime. And again, for that, you have this equation. H prime over H is equal to Q over P, but with a negative sign, which is inherent to the equation. So don't change that. It's already inherent to the equation. So H prime is equal to negative Q over P times H, which gives me negative Q is, sorry, nice ayop. Negative 2.5 divided by 3.5, that gives me negative. So this should be negative. So this should be negative 0.71 inch over your P, remember, is 1 inch. Positive, and again, positive means it is in front of the mirror. Times H, which is 1.5 inches or inch. Okay, so calculating that, that's 0.71 times 1.5. That gives me, let's just ignore this negative sign first. So that gives me negative 1.065 inches squared divided by 1 inch. And again, similar story. The inch here cancels out with one of the inches in the inches squared. So that gives you 1 inch. So the H prime is, well, anything divided by 1 is just 1, right? And then negative and positive, negative and negative becomes positive. So that gives me 1.065 inch. Okay? So now I can go to the lost analysis. So number one, I would say, what's the location? Well, the location is negative 71. What's negative 71? Again, negative glass means inside the mirror. So we measure 0.71 inside. So 0.71 inside is somewhere here, which is obviously between V and F. So I would say inside the mirror between V and F. Okay. Then what is the orientation? Well, I'll just look at the height. The sign is positive. So it must be upright. How about the size? Well, I compare the original height, which is 1.5. I compare it to the height now, which is 1.065. So it should be smaller. Now, how about the type? Again, the type is based on the sign of the Q. Because if the sign is negative, that means the image is formed inside the mirror. Remember, negative sign means inside the mirror. If it's positive, then it's formed outside the mirror. If it's formed outside the mirror, it must be real because light rays can be there. But inside the mirrors, light rays cannot be there, so it should be an imaginary image or a virtual image. The fact that it is negative, that means it must be a virtual image. Okay? So remember, you did all of this just by calculation. So now we have to do it by ray diagramming. And let's confirm if these, because these are interpretations that we had just from the calculation, if these are correct. Okay? So again, first ray, PF ray, parallel ray. So you have to make your ruler parallel to the principal axis, principal axis. You have to hit it, make the light ray hit the mirror, and then as it hits the mirror, it will align with the focus. Remember, it cannot penetrate the mirror, so it cannot go inside, but it will align with the focus. It cannot go to the focus and pass through the focus. It will align with the focus, so it will be reflected this way. That's the PF ray. Now, how about the V ray? So the V ray is here towards the vertex. Sorry, hits the vertex. And again, when it hits the vertex, you kind of have to judge this angle here, and you might make the other angle. So the best way to do that is just measure your height here. So your height here is one inch. So you kind of make a label of where 1 inch is on the other side. Then from there, make your line. So that's your V ray. Now you have your FP ray, which is your ray that is aligned with the focus on the other side. Hits the mirror, does not really go in there, and then becomes parallel to the principal axis. So then finally you have the CC ray, which is a ray that is aligned with the center of curvature, right? And again, it doesn't really go in because it's an opaque material. It just goes in and then gets reflected on the same line. Okay? Then finally, how do you make the ray diagram? Well, again, you trace the reflected ray. So this is important. Reflected ray. You do not trace the incident ray. So what I mean by that is this. This is incident, reflected. So you do not trace this incident ray. What you trace is the reflected ray. So this is the reflected ray here. Obviously, when you trace it back, it should, align with the focus. And then, how about the V ray? Well, V ray is incident, reflected. So you trace the reflected ray. So this one. How about the PF ray? The FP ray. FP ray. So you trace back the P ray. And then how about the CC ray? Well, again, you trace back the. So this is the incident, reflected. So you trace back the reflected ray. Okay. And then now notice where they meet. So they seem to meet here, right? Now you look at the V-ray. The V-ray is not aligned with the 3, but majority of the 3 is aligned here. And again, this is important, class, that we get errors like that because, again, we are using a spherical surface and not a parabolic one. If we were using a parabolic one, then this would be perfect. But because we are using a circular and the length that we had is quite big, the length of the object is quite big, so it affects the one. But in cases like this, you simply have to kind of estimate that, okay, the 3's are here, so it must be here. But you ignore the ray that is not giving you an accurate result. So again, top of the arrow, top of the arrow, foot of the arrow, foot of the arrow should be on here. So this is your object, this is your image. Okay? So moment of truth. If the loss that we found out here should be the same as the loss that we will find from the ray diagramming. So number one, location. Well, it's between V and F. And it's inside the mirror. So inside the mirror between F and V. Okay? How about the orientation? Well, you know that it's upright. It's not inverted. How about the size? Well, this is the original size. This is the size of the image. It's smaller. How about the type? Well, you see that this is image is formed by retracing the light rays. It's inside the mirror, so it should be virtual. Okay? And if you even want to be accurate, we can measure the distance of the Q. Because here we calculated Q to be 0.71, negative 0.71. So we can measure that. And it might not be accurate again because of the nature of our curve, which is not parabolic, but it gets close. So look at that. 0, this is 1 inch. It doesn't reach the 1 inch part. So therefore, it should be less than 1 inch, less than 1 inch as calculated. How about the height? The height should be around 1 inch, right? Or more than 1 inch. So if you look at the height here, it's like that, 1 inch more. And again, there is some inaccuracies because we are doing ray diagrams and we are using not a parabolic surface. Okay? So, but the point that I'm trying to say here is that generally the ray diagram and the mathematical method agrees with their results. Okay? So on your performance task, that is what you do. So typically you will have this uh, the ray diagramming part on one page, and then all the mathematical part on the other page. Okay, it doesn't have to be back to back, but because after all you will submit this digitally, so it doesn't really matter if you make if you do them back to back. But the one page would be ray diagrams with a lost description, and then the second page will be all the mathematical method but still with the lost here. So I think that would be all. And again, please take note, you will be doing 5 cases depending on whether you are assigned to do lens or mirror and whether you're assigned to do concave or convex. You will do 5 cases, which is again beyond 2F or beyond C, between 2F and F, or between 2C and F, at C or at 2F, be at F or at, and between F and V. Okay, so to make your life easier, I will send a table of those locations, object locations, so that you will not be confused. Okay, so I think that would be all for this video. Thank you, and I hope you understood the performance task by now.